Okay, so another application of partial derivative would be how can you find the local extrema? Okay, so I think as an engineering students, okay, you have learned previously, okay, that finding maximum or minimum values of a function is important, okay, due to its practical application. Okay, so you can actually refer to this to this teaching notes. Okay, so this is based on the graph sketching of any kind of a given surface, I would say. Okay, so it can be either maximum or minimum point, okay, based on the surface as well as the point that we figure out. Okay, and another types of play the point that can be considered, we call as a saddle point. Okay, so this is the interpretation of the saddle point. Okay, so I think when we talk about maximum and minimum, okay, so whenever we have a graph sketching, it will be easy to identify if we have if we have a correct sketching. Okay, but what if we have a multi-variable function that is complicated to sketch, for example? Okay, so partial derivative is one of the way on how can you figure out those point. Okay, so first thing first, okay, so we're gonna learn on how can we find that local extrema point. Okay, so or another way is we call as a critical point. Okay, so the critical point. Okay, so we're going to use this theorem. Okay, so by using the partial derivative respect to x and respect to y equal to 0. Okay, so if we solve this one, okay, both this partial derivative respect to both, okay, independent variable means that equal to 0. Okay, so you're going to get that critical point. Okay, so for a given surface of a given function, okay, it's not necessarily just a one critical point. It can be more than two, more than three, for example. Depends on the given function. Okay, so when we have that critical point, okay, so the next is how can we actually differentiate, okay, which one is the maximum, which one is the minimum, or which one is the saddle point. Okay, so the next step, okay, so we're going to use second derivative test, okay, in order for us to classify, okay, the critical point that we figure out, okay, based on the theorem that I introduced in the previous slide. Okay, how can we differentiate? Okay, so we're going to use this by find values of g over here. Okay, so from here, we're gonna have four types of conclusion. Okay, so whenever we have that the values of g, okay, is greater than 0, okay, plus with the values of f x, okay, is less than 0, you're gonna have a local maximum. Okay, but then if the values of g, okay, is greater than 0 but that f(x) is greater than 0, so the point that you have is a, sorry, I think this one is mistypo, so this one should be is local maximum. Okay, so this one is local minimum. Okay, so this should be local minimum. Okay, because we have difference over here, even though the values of g is now positive. But what if the values of g that we figure out is less than 0? Okay, so if you have the values of g is less than 0, so you can directly conclude that the critical point that you figure out is a saddle point. Whereas if the values of g, okay, that you got is equal to 0, means that is there is no conclusion for that particular point that you figure out. Okay, so this is the part of we call it as second derivative test. Okay, so this is the formula, okay, in order for you to find the values of g over here. So we're gonna use the prior knowledge on the higher order partial derivative that we have learned in the previous subtopic in order for us to proceed, okay, with this second derivative test. Okay, so I did pinpoint over here. Okay, how should you figure out in order to get the critical point? Okay, so if we compare, okay, the left side and right side over here, okay, so if you solve it like this, okay, means that you rearrange the terms, okay, you will definitely get only two values of x, okay, but this is wrong, okay, so it should be solved like this, okay, so from here you're gonna have 3 points, okay, like I said, okay, it's not only 1 point, normally depends on the function that we give to the student. Okay, so let's take a look on the first example. Okay, I will show you on how can we find the critical point first before we use second derivative test in order for us to classify each critical point that we figure out, okay, whether it's a local maximum, local minimum, or a saddle point. Okay, so let's take a look on the first one. Okay, so we have a function of a multivariable function. We have 2y to the power of 3 minus 6xy minus x squared. Okay, so the first step in order for us to get the critical point is to find the partial derivative respect to each independent variables. Okay, so since this one involved with two independent variables, okay, so let's figure out the partial derivative respect to x. Okay, so you're gonna get negative 6y minus 2x equal to 0. So this will be the first equation. Okay, so the next one is fy. So now we're going to differentiate respect to y. So we're going to have 6y to the power of 2 minus 6x equal to 0. Okay, so from here we're going to solve it. Okay, the way you solve, okay, in order for you to get the critical point is depends on your creativity on how can you solve it. Okay, because we need to solve for both. Okay, so this is how I solve for this one. Okay, so for example, if I take the first equation, okay, from 1, okay, so we have negative 6y minus 2x equal to 0. Okay, so if I make x as a subject, so we're going to have 6y over here and x is equal to negative 3y. Okay, so let's set this one as the third equation. Okay, so if you substitute, okay, if we substitute this equation into this one, okay, so from equation 2, so we have 6y squared minus 6x equal to 0. Because our intention is for us to get the critical point, right? So means that you have to find the possible critical points in terms of x and y, the values of x and y. Okay, so we have x in terms of y, so we're going to substitute, okay, into this one. So we have 6y squared minus 6 multiplied with negative 3y equal to 0. Okay, so if you solve for this one, if you simplify, so you're going to get 6y squared plus y equal to 0. Okay, so from here, okay, we're going to take out y over here, so we have 6y plus 18 equal to 0. So from here we knows that, okay, so we knows that y, okay, let me write it back. So we have y 6y plus 18 over here equal to 0. I write like that. Okay, so from here we know that this one is equal to 0 and this one also equal to 0. So we have y equal to 0, the first values of y, and another one is 6y plus 18 equal to 0. So from here, you're going to get y is equal to negative 3. So based on the given function, the first one, okay, so the values of y would be y equal to 0 and y equal to negative 3. So now, we're going to substitute back these values, okay, into this one in order for us to get the values of x. Okay, so since we know that x is equal to negative 3y just now, right? So whenever y is equal to 0, so you're going to get x also 0. Okay, so when y is equal to negative 3, so you're going to get that x is equal to 9 over here. So the critical point for the given first function would be 0, 0. And then another one would be 9, negative 3. Okay, so since we involve with a function with independent two independent variable, right? Okay, so another point should be like this, right? X, y, and z. Okay, so if you would like to get the values of z, you just substitute the values of x and y that you figure out into this original function. So you will definitely get like this, 0, 0, 0. And for this one, 9, -3. Over here would be 27. Okay, but if you just give the answers like this, also possible. Okay, instead of you give like this. Okay, but you should know how should you get the values of z over here. It's coming from the original function. Okay, so if the question asks you to list the critical point, you should know that this is the critical point for the given function. Okay, so now we're going to use second derivative test in order for us to classify, okay, from these two critical point, whether it's a local maximum or minimum or saddle point. Okay, so let's take a look on the original, let's take a look on this one. Okay, so we have figured out fx just now is equal to -6y minus 2x. Fy is equal to 6y squared minus 6x. Okay, so based on this one, okay, so you need fxx. Okay, so fxx, you're gonna have -2. Okay, and then fyy that you need, you're gonna have 12y. Okay, so you need to have the mixed higher order as well for fyx and fxy. But we knows that, okay, we knows that this one you're gonna have the same terms. Okay, so from here, you're gonna get that. For example, if we would like to find fxy, okay, so from this one, okay, so you're gonna get -6. Okay, so let me prove. Okay, if we differentiate from here to get fyx, so you're gonna get -6 as well. Okay, make sure that you show clearly for this part. Okay, and then put it into the formula for g. Okay, so you're gonna have like this. Okay, so -2 for fxx over here would be -6. Same goes to for this part, and for this part would be 12y. Okay, so if you solve for this one, so the formula in order for us to get the values of g for each critical point that we figure out will be -24y minus 36. So we're gonna use this one, okay, to check for every critical point that we got. Okay, so let's start with the first one, 0, 0. So the values of g when x and y is equal to 0, so you're gonna get -36. Okay, so from here, we know that -36 is less than 0. So based on this conclusion, so we know that whenever g is less than 0, you can directly, okay, conclude that this critical point is a saddle point. Okay, so from here, we know that 0, 0 is a saddle point. Make sure that you write it clearly. Okay, so the next one. Okay, so the next one is just now 9, -3. Okay, so if we would like to find the values of g over here, so you're going to get for this part would be 36. Okay, so we know that 36 is greater than 0. Okay, so let's take a look on this one. Okay, on the first option and the second option. Another condition that need to be considered is depends on fxx. Okay, so based on this one, so we know that, okay, for this function, fxx is equal to -2, which one less than 0, which are less than 0. So it's gonna fall into this condition, right? So it means that this point 9, -3 is a maximum, local maximum point. Okay, so that's how, you solve, okay, or you finally declare, okay, by using second derivative test for each critical point that you figure out. Okay, so let me show one more example. Okay, so I have shown for the first one. Okay, so let me show for the second part. Okay, second question. Okay, so for the second question, okay, so we have a function over here. is equal to 1 over 3 y to the power of 3 minus x square minus y. Okay, so from here, let's find the critical point. So the partial derivative respect to x, you're going to get negative 2x equal to 0. So this will be the first equation. Okay, so the second one, partial derivative respect to y. So over here, you're going to get y squared minus 1 equal to 0. So this will be the second equation. Okay, so from here, okay, from equation 1, so you will definitely get negative 2x equal to 0. So x is equal to 0. Okay, so from equation number 2, so we have y squared minus 1 equal to 0, right? So if we rearrange, so you're going to get y squared equal to 1. Okay, so from here, okay, so the possible values of y would be plus minus 1. Means that if y negative 1, you can also get 1, right? Which means that it satisfied this function. This equation. Okay, so means that there is 2 possible values of y over here. Okay, so we know that the critical point for this given function would be 0, 1 and 0, negative 1 based on this solution. Okay, so the next one, we're going to figure out the formula for g. Okay, so we know that we need fxx, right, over here. So let's take a look on this one. Okay, so if you differentiate this one for one more time, so you're going to get negative 2. Okay, so the first the terms for here is fxy and fyx. So from here, if you differentiate respect to y, so you're going to get 0. So 0 for this part, 0 for this part as well. And the last one is for you to figure out fyy. So you're going to get 2y over here. So the formula in order for you to figure out the values of g would be negative 4y. Okay, so I'd like you to continue for this part. Okay, so based on this one, if you calculate the values of g, okay, for each critical point that you figure out, okay, you should know that, okay, 0, 1 is a saddle point. And the second point, 0, negative 1, is a local maximum point. Okay, so I would like you to continue for this one. Okay, so I did give you a clear explanation on the first question. Okay, so I'd like you to continue by your own until you can achieve this conclusion. Okay, and then for the last question, okay, so I'll just share with you guys for the critical point. Okay, so for this one, you should have 3 critical point over here. Is 0, 0. Okay, the next one is 2, negative 2. And then the last one is negative 2, 2 over here. Okay, so from here, I want you to try to solve by your own, okay, for C, okay, whether you be able to get this critical point or not before you move to second derivative test, okay, for you to classify that critical point you figure out falls into which category, whether it's a local maximum, local minimum, or saddle point. Okay, so as an additional infos, okay, so since we are dealing with the application of partial derivative, okay, so it's very rare cases that when you calculate for the values of g, you got 0, means that there's no conclusion. It's very rare cases. Okay, we'll make sure that the values, you're gonna have the values of g. So whenever that you answer the question, you got g equal to 0, there must be something wrong with your higher order partial derivative. So please check that. Okay. Okay, so I did also give you an exercise over here. Okay, so this is the sample of task, okay, together with the answers that you need. Okay, so that's all for this video. Thank you.